So in the last video, we've seen how to interpret the estimated regression results. And then also what is going to happen to the coefficient estimate if there is some kind of change in the x or the y. So for instance, if you double the values of the dependent variable, then what do we expect will happen to the slope? Or if we double the values of the independent variable, what should happen to the slope? All right, so, and this time around we'll also talk more on the validity. Okay, so how we can verify the veracity of the results you have. So there are two ways that you can do that. But this is how we're going to start. So we need to go back to the original model. All right. So again, we're still going with the case where the dependent variable is income. Okay, and we're regressing it on the age. We have the error. Okay, good. So if we end up estimating this model, okay, if we end up estimating the model, then we're going to have something like this. If we estimate the model, we're going to have an estimated value for alpha. Okay, and we're going to have an estimated value for the beta and the age. Okay, so if you estimate the value of alpha and beta, then you're going to have something like this, all right? And that becomes the estimated model. So the hat on top is just to let you know that this is the estimated model. All right, good. And of course, that is going to be whatever we cannot estimate. Whatever we cannot estimate, basically go into the error term. All right. Good. So the point I'm trying to make now is that any regression model we can decompose into two parts. Okay? We can decompose the regression model into two parts. Okay. So the part is what we have, the first part is what we have control over. Okay, so for instance, if you run this model, it's basically estimating this. That is what your model can explain. Okay, you're able to find the alpha and the beta. Okay, so your model is the part that your model can explain. All right, and then this part is the error. So your model cannot explain that because there are so many factors that affect income which we didn't include in the model, so they all go into the error, so we don't have control over that. Okay, so yeah, so the point I'm trying to make is that the total change, okay, so the total change in income is something that we can decompose into two, right? So the first part is the part that we can explain, okay? The part we can explain. So I'm going to call it the explained. So that is the part our model can explain. Plus, the second part is the part we cannot explain, which is the error, right? So I'm going to replace it with unexplained. Right. So yeah, so what I'm going to do now is I'm going to use the total to divide both sides. So what do I mean? We have total changing income here, so I'm also going to divide by the same total. I divide by the total, I divide by the same total change in income. All right, so what does that mean? It means this whole part becomes just a 1. Okay, and then this becomes the proportion of the variation in the dependent variable which we are able to explain. Okay, so I'm going to call it the explained variation. Okay, so the explained variation, the changes in the dependent variable which we're able to explain. All right, and then this becomes the unexplained variation. Okay, so where are we heading to? We want to verify the veracity of what we have. Okay? We want to verify the veracity of what we have. So you see that one way you can do such verification to verify whether your model performed very well or not is by just focusing on this. Okay, you just need to focus on the part your model is able to explain. Okay, so if that explained component is large enough, then it means that the model did very well in explaining the changes in the dependent variable. Okay, so I mean, since the total adds up to 1, then of course it means that whatever this is going to be, it should be something that ranges from 0 to 1. Okay, so it wouldn't exceed that. Yeah, so the explained variation is now going to be 1 minus the unexplained. Okay, and it is this that we call the so-called R square. Okay, so that is the so-called R square in regression. So the R square basically tells you the proportion, okay, the proportion of the variation in the dependent variable which is explained by your model. Okay, so in this case, which is explained by the age. Right, it tells you the proportion of the changes in the dependent variable that is explained by your model. So you see, the implication is if there are so many factors that you didn't include in the model, which all go into the error term, then the unexplained variation becomes larger. And if it's getting larger, then the explained component becomes smaller. Okay? So the explained component is going to get smaller when you commit more errors. All right. So yeah, so that is one way. Okay, so whenever you run your model, if you're using a statistical software, okay, so one of the things it's going to report to you would be an R square. Okay, so you can see a value 0.3 something, you can see 0.6, 0.9, it can be anything, right? It can be anything. So those are just proportions. So in the case of 0.32, then that would mean that the model you estimated is able to explain only 32% of the changes in your dependent variable. And this will mean that your model is able to explain only 60%. And here, the model is able to explain 90% of the changes in the dependent variable. Okay? So for sure, you definitely want the situation where that number should be getting larger and larger. Okay? Because if it's getting larger, then it means that your model is doing really good in explaining the changes in the dependent variable, which of course also means that you're not making much errors. All right. Yeah, so it means that you're not making much errors in your estimation. So that is one way you can determine whether your model did really well. Okay. So that is big enough, but of course we don't really know. There is no yardstick for determining whether it is large enough or whether it is small. So it's now something you have to do by yourself. So yeah, but there is one thing I do have to point out regarding this R square. Okay. So if you notice, I keep saying that if there are so many factors you didn't add to your model, that they're going to go into the error term, right? I keep saying something like that. So I'm going to put this income plus, so income equals alpha plus beta 1 age. Okay, I'm going to go there and put my error. And I keep saying that if there are factors that you didn't add to this model, they're going to go into the error. Okay, and if that error is getting larger and larger, then your ability to accurately estimate the beta one becomes smaller and smaller. All right. So, but if you want to reduce the errors you're making, then all you have to do is think of all those variables in the error term, okay, that are correlated with your age, which is the main independent variable. So think of all those omitted variables in the error that are correlated with age. Okay, so if you know them, just keep adding them in the model. Okay, so as you're adding them, it's going to allow you to accurately estimate the value of beta 1. So please note, even though you're adding them, you don't really care about the coefficient estimate. Okay, so the point of you adding them is because you want to make sure that you're accurately estimating the value of beta 1. So yeah. So let's do the thinking now. One of the omitted variable here is obviously education. Okay, but do remember, it will only make sense to add that to the model if it is correlated with your main independent variable, age. So think of it, is education correlated with age? Of course, they're correlated. So take someone that is 1 year old, take someone that is 30 years old. Would you expect to have higher years of education? So it is obviously someone that is 30 years old. Okay, so education should be positively correlated with age. So that means it needs to be here. So what do? You say beta 2, you add the education. Okay, beta 2, you add education. Okay, then think again, is there any other factor that we're missing that should be in the error term? And the potential thing could be the experience. Okay, so we tend to say that with age comes wisdom. So experience is obviously an important factor here. So we can also control for it. We add beta 3, we add experience. Okay, so you can just, if you know all that you can think of, right? And then a beta 4, you can also add a gender dummy variable. So just keep adding things. Okay, but of course, no matter what you do, you cannot control every one of them. Okay, so there are variables out there that, even though deep down you know that they are correlated with age and affect income, but you don't really know how you can measure them. Okay, you don't really know how you can measure them. So there's that. Yeah, so that's how you can add more things. So as you're adding more and more of them, the error is going to be getting smaller. Okay, and of course, so the error, which is the unexplained part, will be getting smaller. And if it's getting smaller, it means that the explained part is getting larger. So the implication is, as you're adding more and more important variables that affect the dependent variable, then the R square is going to be getting larger. Okay, so it's as simple as that. If you're interested in a very high R square, then keep adding more control variables to your model. Okay, but one problem with this R square is that it is highly sensitive to what you're adding. Okay, it is highly sensitive to what you're adding. So far you keep adding more and more variables, so it will be responding to such addition. Okay, so you can even add something that is completely meaningless. Okay, that is totally unrelated to the model you have, and the R square is going to respond to that by going up or going down. Okay, so for instance, suppose there is a way for us to measure, the number of times someone cried in a day or in a year. Okay, so suppose there is a way to measure the number of times, okay, someone cried. Okay, the number of times someone cried. Okay, or let's say the number of slaps, okay, received. Okay. So the number of slaps received in a year. Okay, suppose that is a way to count that, to measure that. If we add it to the model, the R square is going to respond. Okay, so you see that is a problem. because you're adding things that are basically not related, they're not important, but yet the R square is telling you that, yeah, the model is doing very well. Okay, and we don't want something like that. All right, we don't want the R square to be that sensitive to the addition of irrelevant variables. So that's why there is an alternative measure. So there is something called the adjusted R square. Okay, so that's why there is the adjusted R square. So the adjusted R square is derived from the R square. Okay, but what does the adjusted mean? So it means that some adjustment has been made to make the R square to be less sensitive. Okay, to the additions you're making. All right. So in most published research papers, people will tend to prefer the adjusted R square. Okay, so if they want to judge whether your model did very well, okay, so they will tend to prefer looking at the value of the adjusted R square. Again, and you don't really need to worry about this. So if you do the estimation using any statistical software, so that software will tend to publish pretty much everything you need, including the R square and the adjusted R square. Okay, and if you see that in most, yeah, you tend to see that the R square will be higher than the adjusted R square. Okay, so the R square will tend to be higher than the adjusted R square. So that's why the R square is more believable. It has made adjustments. The adjusted has made adjustments so that it is no longer that sensitive to the additions you're making. All right. Yeah. So that's that. Okay. So that is one way you can judge the validity of what you have. Then an alternative way is you can just focus on the error, right? You can focus mainly on the error, which of course account for all those factors you didn't add, okay? So you can simply focus on the error and then just calculate its standard deviation, okay? So calculate the standard deviation of your error, okay? So, I mean, if that number is large, then it really means that you're making a lot of mistake in your estimation. But if it's small, then that's good. And of course, they're all related, right? So whenever your R square is low, okay, if your R square is small, then your standard deviation of your error should be larger, right? But if the R square is big, then the standard deviation, the errors you're making will have to be small, right? So that the relationship is always there. So again, if you estimate your model is going to publish the error as well, okay? So the mean square error, okay? So that is also something you can use to judge the performance of your model. Okay, but the only problem with these things is, I mean, it doesn't really provide you a yardstick, which you can always use to judge whether you have something high or something low. Okay, so it really comes down to you, the researcher or the person doing the estimation, to make that decision whether you have a high R square or a low R square, or a high standard deviation of the error term, or low standard deviation. All right, so yeah, so it's not just about you estimating the model, you see the alpha and beta and you're done. No. So you also have to ask yourself if your model performed really well in explaining the dependent variable. So that is something that we're particularly interested in. Right. So that's that. So again, I'll keep posting videos on a weekly basis. So in a week, I should be able to post at least 3 long videos, right? And also, I believe the next video I'm going to post, so I'm going to use theta to estimate these things so that you can see how they are done using statistical software.